started in a moment, since it's now 12:30. Are there any questions before we get started? Okay, I don't see any, so I guess we can jump right in. This time I'll be talking about sequence modeling, and first I'm going to be talking about why we do sequence modeling, what varieties of sequence modeling exist, and then after that I'm going to talk about kind of three basic techniques for sequence modeling, namely recurrent neural networks, convolutional networks, and attention. So when we talk about sequence modeling in NLP, I've kind of already made the motivation for doing this, but basically NLP is full of sequential data. And this can be everything from words and sentences or tokens and sentences to characters and words to sentences in a discourse or a paragraph or a document. It can also be multiple documents in time, multiple social media posts, whatever else you want. There's just sequences all over NLP. And I mentioned this last time also, but there's also long distance dependencies in language. So just to give an example, there's agreement in number, gender, etc. So in order to create a fluent language model, you'll have to handle this agreement. So if you say he does not have very much confidence in, it would have to be himself. But if you say she does not have very much confidence in, it would have to be herself. And this gender agreement is not super frequent in English, but it's very frequent in other languages like French or most languages in the world in some way or another. Then separately from that, you also have things like selectional preferences, like the rain has lasted as long as the life of the queen, and the rain has lasted as long as the life of the clouds. In American English, the only way you could know which word came beforehand if you were doing speech recognition is if you had that kind of semantic idea of that these agree with each other in some way. And there's also factual knowledge. There's all kinds of other things that you need to carry over long contexts. These can be complicated. So this is a nice example. So if we try to figure out what it refers to here, the trophy would not fit in the brown suitcase because it was too big. What is it here? The trophy, yeah. And then what about the trophy would not fit in the brown suitcase because it was too small? Suitcase, right. Does anyone know what the name of something like this is? Has anyone heard of this challenge before? No one? Okay. This is called the Winograd schema challenge, or these are called Winograd schemas. And basically, Winograd schemas are a type of kind of linguistic challenge where you create two paired examples that you vary in very minimal ways, where the answer differs between the two. And so there's lots of other examples about how you can create these things, and they're good for testing whether language models are able to do things, because they're able to kind of control for the fact that, like the answer might be, the answer might be very like more frequent or less frequent, and so the language model could just pick that. So another example is we came up with a benchmark of figurative language where we tried to figure out whether language models would be able to interpret figurative language. And I actually have the multilingual version on the suggested projects on the Piazza. Oh yeah, that's one announcement. I posted a big list of suggested projects on Piazza. I think a lot of people saw it. You don't have to follow these, but if you're interested in them, feel free to talk to the contacts and we can give you more information about them. But anyway, so in this data set, what we did is we came up with some figurative language, like this movie had the depth of a wading pool, and this movie had the depth of a diving pool. And so then after that, you would have two choices. This movie was very deep and interesting. This movie was not very deep and interesting. And so you have these like two pairs of questions and answers, and you need to decide between them. And depending on what the input is, the output will change. And so that's a good way to control for and test whether language models really understand something. So if you're interested in benchmarking or other things like that, it's a good paradigm to think about. Anyway, that's a little bit of an aside. So now I'd like to go on to types of sequential prediction problems. And types of prediction problems in general, binary and multi-class we already talked about. That's when we're doing, for example, classification between two classes or classification between multiple classes. But there's also another variety of prediction called structured prediction. And structured prediction is when you have a very large number of labels. It's not, a finite number of labels. And so that would be something like if you take in an input and you want to predict all of the parts of speech of all of the words in the input. And if you had like 50 parts of speech, the number of labels that you would have for each sentence is, any ideas? 50 parts of speech and like, let's say 4 words. 60? It's every combination of parts of speech for every word. So close, but maybe the opposite. It's 50 to the 4 because you have 50 choices here, 50 choices here. So it's a cross product of all of the choices. And so that becomes very quickly untenable. Let's say you're talking about translation from English to Japanese. Now you don't really even have a finite number of choices because the length could be even longer. The length of the output could be even longer than that.
So in general, like 50 types of parts of speech, but do they follow certain rules that these two cannot be connect together? Like these two have the truth, which makes it like fewer than the.
Yeah, so really good question. So the question or comment was, if there are certain rules about one thing not ever being able to follow the other, you can actually reduce the number. You could do that with a hard constraint and make things kind of like actually cut off things that have 0 probability. But in reality, what people do is they just trim hypotheses that have low probability, and so that has kind of the same effect. Like you almost never see a determiner after a determiner in English. And so, yeah, we're going to talk about algorithms to do this in the generation section. So we can talk more about that then. But anyway, the basic idea behind structured prediction is that you don't, like language modeling, like I said last time, you don't predict all of the whole sequence at once. You usually predict each element at once and then somehow calculate the conditional probability of the next element given the current element or other things like that. So that's how we solve structured prediction problems. Another thing is unconditioned versus conditioned prediction. So unconditioned prediction, we don't do this very often, but basically we predict the probability of a single variable or generate a single variable. And conditioned prediction is predicting the probability of an output variable given an input like this. So for unconditioned prediction, the way we can do this is left to right autoregressive models. And these are the ones that I talked about last time when I was talking about how we build language models. And these could be specifically this kind, though, is a kind that doesn't have any context limit. So it's looking all the way back to the beginning of the sequence. And this could be like an infinite length n-gram model, but practically we can't use those because they would have too many parameters. They would be too sparse for us to estimate the parameters. So what we do instead with n-gram models, which I talked about last time, is we limit the context length. So we have something like a trigram model where we don't actually reference all of the previous outputs when we make a prediction. Oh, and sorry, actually, I should explain. How do we read this graph? So this would be, we're predicting number 1 here. We're predicting word number 1, and we're not conditioning on anything after it. We're predicting word number 2. We're conditioning on word number 1. We're predicting word number 3. We're conditioning on word number 2. So here we would be predicting word number 4. conditioning on words number 3 and 2, but not number 1. So that would be like a trigram model. So the what is this? Is there a robot walking around somewhere? Power drill. Okay. Be a lot more fun if it was a robot. So the things we're going to talk about today are largely going to be ones that have unlimited length context. And so we'll talk about some examples here. And then there's also independent prediction. So this would be something like a Winograd model where you would just not condition on any previous context. There's also bidirectional prediction, where basically when you predict each element, you predict based on all of the other elements, not the element itself. This could be something like a masked language model. But note here that I put a slash through here because this is not a well-formed probability, because as I mentioned last time, in order to have a well-formed probability, you need to predict the elements based on all of the elements that you predicted before, and you can't predict based on future elements. So this is not actually a probabilistic model, but sometimes people use this to kind of learn representations that could be used downstream for some reason. Cool. Is this clear? Any questions, comments? Yeah. So these are all not conditioning on any prior context. Yeah. So when you predict each word, it's conditioning on context that you previously generated or previously predicted. Yeah. So, and if I go to the conditioned ones, these are where you have like a source X, where you're given this, and then you want to calculate the conditional probability of something else. So, to give some examples of this, this is autoregressive conditioned prediction. And this could be like a standard sequence to sequence model, or it could be a language model where you're given a prompt and you want to predict the following output, like we often do with ChatGPT or something like this. And so, yeah, I don't think you can. Yeah, I don't know if any way you can do ChatGPT without any conditioning context. But there were people who were sending, I saw this about a week or two ago, there were people who were sending things to the to the GPT 3.5 or GPT-4 API with no input, and it would randomly output random questions or something like that. So that's what happens when you send things to ChatGPT without any prior conditioning context. But normally what you do is you put in your prompt, and then it follows up with your prompt, and that would be in this paradigm. There's also something called non-autoregressive condition prediction, and this can be used for something like sequence labeling or non-autoregressive machine translation. I'll talk about the first one in this class, and I'll talk about the second one maybe later. It's kind of a minor topic now. It used to be popular a few years ago, so I'm not sure whether I'll cover it, but yeah. Cool. So the basic modeling paradigm that we use for things like this is extracting features and predicting. So this is exactly the same as the bag of words model, right? The bag of words model that I talked about the first time, we extracted features. Based on those features, we made predictions. So it's no different when we do sequence modeling, but the methods that we use for feature extraction is different. So given an input text X, we extract features H and predict labels Y. And for something like text classification, what we do is so for example, we have text classification or sequence labeling. And for text classification, usually what we would do is we would have a feature extractor. From this feature extractor, we take the sequence and we convert it into a single vector. And then based on this vector, we make a prediction. So that's what we do for classification. For sequence labeling, normally what we do is we extract one vector for each thing that we would like to predict about. So here, that might be one vector for each word. And then based on this, we would predict something for each word. So this is an example of part of speech tagging, but there's a lot of other sequence labeling tasks also. And what tasks exist for something like sequence labeling? So sequence labeling is a pretty big subset of NLP tasks. You can express a lot of things as sequence labeling. And basically, given an input text X, we predict an output label sequence Y of equal length. So this can be used for things like part of speech tagging to get the parts of speech of each word. It can also be used for something like lemmatization. And lemmatization, basically what that is it is predicting the base form of each word. And this can be used for normalization if you want to find, like, for example, all instances of a particular verb being used or all instances of a particular noun being used. This is a little bit different than something like stemming. So stemming, normally what the stemming would do is it would chop off the plural here. It would chop off S, but it wouldn't be able to do things like normalize saw into C because stemming just removes suffixes. It doesn't do any sort of normalization. So that's the difference between lemmatization and stemming. There's also something called morphological tagging. In morphological tagging, basically what this is doing is this is a more advanced version of part of speech tagging that predicts things like, okay, this is a past tense verb. This is a plural. This is a particular verb form, and you have multiple tags here. This is less interesting in English because English is kind of a boring language morphologically. It doesn't have a lot of conjugation and other stuff, but it's a lot more interesting in more complex languages like Japanese or Hindi or other things like that. Chinese is even more boring than English. So if you're interested in Chinese, then you don't need to worry about that. Cool. But actually, what's maybe more widely used from the sequence labeling perspective is span labeling. And here you want to predict spans in labels. And this could be named entity recognition. So if you say Graham Neubig is teaching at Carnegie Mellon University, you would want to identify each entity as being like a person, organization, place, governmental entity, other stuff like that. There's also things like syntactic chunking, where you want to find all noun phrases and verb phrases. Also semantic role labeling, where semantic role labeling is demonstrating who did what to whom. So it's saying this is the actor, the person who did the thing. This is the thing that is being done, and this is the place where it's being done. So this can be useful if you want to do any sort of analysis about who does what to whom, other things like that. There's also a more complicated thing called entity linking, which isn't really a span linking task, but it's basically named entity recognition, and you link it to like a database like Wikidata or Wikipedia or something like this. And this doesn't seem very glamorous, perhaps. You know, a lot of people might not sound like be immediately excited by entity linking, but actually it's super, super important for things like news aggregation and other stuff like that. Find all the news articles about this celebrity or something like this. Find all of the mentions of our product, our company's product in social media or things. So it's actually a really widely used technology. And then finally, span labeling can also be treated as sequence labeling. And the way we normally do this is we use something called BIO tags. And here you predict the beginning, in, and out tags for each word or span. So if we have this example of spans, we just convert this into tags where you say begin person, in person. O means it's not an entity, begin organization, in organization. And then you can convert that back into these spans. So this makes it relatively easy to kind of do the span prediction. Cool. So now you know what to do if you want to predict entities or other things like that. And there's a lot of models on like Hugging Face, for example, that allow you to do these things. Are there any questions before I move on? Okay, cool. I'll just go forward then. So now I'm going to talk about how we actually model these in machine learning models. And there's three major types of sequence models. There are other types of sequence models, but I'd say the great majority of work uses one of these three different types. And the first one is recurrence. What recurrence does is it conditions on representations on an encoding of the history. And so the way this works is essentially you have your input vectors like this, usually word embeddings or embeddings from the previous layer of the model. And you have a recurrent neural network. And the recurrent neural network at the very beginning might only take the first vector, but every subsequent step, it takes the input vector and it takes the hidden vector from the previous input. And then you keep on going like this all the way through the sequence. The convolution is conditioning representations on local context. So you have the inputs like this. And here you're conditioning on the word itself and the surrounding words on the right or the left. So you would do something like this. This is a typical convolution where you have this certain one here and the left one and the right one. And this would be a size 3 convolution. You could also have a size 5 convolution, 7, 9, whatever else that would take in more surrounding words like this. And then finally, we have attention. And attention is conditioned representations on a weighted average of all tokens in the sequence. And so here, we're conditioning on all of the other tokens in the sequence, but the amount that we condition on each of the tokens differs between them. So we might get more of this token, less of this token, and other things like that. And I'll go into the mechanisms of each of these. One important thing to think about is the computational complexity of each of these. And the computational complexity can be expressed as the sequence length. Let's call the sequence length n. And convolution has a convolution window size, so I'll call that W. So does anyone have an idea of the computational complexity of a recurrent neural network? So how quickly does the computation of a recurrent neural network grow? And one way you can look at this is figure out the number of arrows that you see here. Yeah, it's linear. So it's basically O of n. What about convolution? Any other ideas? Any ideas about convolution? NW. Yeah, NW, n times W. And what about attention? N squared, yeah. So what you can see is for very long sequences, the asymptotic complexity of running a recurrent neural network is lower. So you can run a recurrent neural network over a sequence of length, 20 million or something like that. And as long as you had enough memory, it would take a linear time. But if you do something like attention over a really long sequence, it would be more difficult. There's a lot of caveats here because attention and convolution are easily parallelized, whereas recurrence is not. And I'll talk about that in a second. But anyway, it's a good thing to keep in mind. Cool. So the first sequence model I want to introduce is recurrent neural networks. Oh, sorry. One other thing I want to mention is all of these are still used. It might seem that if you're very plugged into NLP, it might seem like, well, everybody's using attention. So why do we need to learn about the other ones? But actually all of these are used, and usually recurrence and convolution are used in combination with attention in some way for particular applications where recurrence or the convolution are useful. So I'll go into details of that later. So let's talk about the first sequence model, recurrent neural networks. So recurrent neural networks, they're basically tools to remember information. They were invented in around 1990. And the way they work is a feed-forward neural network looks a bit like this. We have some sort of lookup over the context. We calculate embeddings. We do a transform. We get a hidden state, and we make a prediction. Whereas a recurrent neural network feeds in the previous hidden state. And a very simple Elman-style neural network looks or I'll contrast the feed-forward neural network that we already know with an Elman-style neural network, recurrent neural network. So basically, the feed-forward network that we already know does a linear transform over the input, and then it runs it through a nonlinear function. And this could be like a tanh function or a ReLU function or anything like that. In a recurrent neural network, we add multiplication by the previous hidden state. So it looks like this. And so if we look at what processing a sequence looks like, basically what we do is we start out with an initial state. This initial state could be like all zeros, or it could be randomized, or it could be learned, or whatever else. And then based on this, we run it through an RNN function, and then calculate the hidden state, use it to make a prediction. We have the RNN function, make a prediction, RNN, make a prediction, RNN, make a prediction. So one important thing here is that this RNN is exactly the same function, no matter which position it appears in. And so because of that, we just, no matter how long the sequence becomes, we always have the same number of parameters, which is always like really important for a sequence model. So that's what this looks like here. So how do we train RNNs? Basically, if you remember, we can train neural networks as long as we have a directed acyclic graph that calculates our loss function. And then for forward propagation and back propagation, we'll do all the rest to calculate our parameters. And we update the parameters. So the way this works is, let's say we're doing sequence labeling, and each of these predictions is a part of speech. Each of these labels is a true part of speech label. Or sorry, each of these predictions is like a probability over the parts of speech for that sequence. Each of these labels is a true part of speech label. So basically what we do is, from this, we calculate the negative log likelihood of the true part of speech. We get a loss. And so now we have 4 losses here. This is no longer a nice directed acyclic graph that ends in a single loss function, which is kind of what we needed for back propagation, right? So what do? Very simple. We just add them together. We take the sum, and now we have a single loss function, which is the sum of all of the loss functions for each prediction that we made. And that's our total loss. And now we do have a directed acyclic graph where this is the terminal node, and we can do back prop with this. This is true for all sequence models I'm going to talk about today. I'm just illustrating it with recurrent neural networks. Any questions here? Everything good? Okay. Cool. Yeah, so now we have the loss. It's a well-formed DAG. We can run backprop. So basically what we do is we just run backprop, and our loss goes out back into all of the places. Now, parameters are tied across time. So the derivatives into the parameters are aggregated over all of the time steps. And this has been called backpropagation through time since these were originally invented. So basically what it looks like is, because the parameters for this RNN function are shared, they'll essentially be updated. They'll only be updated once, but they're updated from like 4 different positions in this network, essentially. Yeah, and this is the same for all sequence models that I'm going to talk about today. Another variety of models that people use are bidirectional RNNs, and these are used when you want to, do something like sequence labeling. And so you just run 2 RNNs. You run one from the beginning, one from the end, and concatenate them together like this. Make predictions. Cool. And any questions? Yeah.
If you run the bidirectional RNN, does that change your complexity?
Does this change the complexity? It doesn't change the asymptotic complexity because you're multiplying by 2. And like big O notation doesn't care if you multiply by a constant, but it does double the time that it would take. Cool. Any other? Okay, let's go forward. Another problem that is particularly salient in RNNs, and part of the reason why attention models are so useful, is vanishing gradients. But you should be aware of this regardless of whether, like, no matter which model you're using. And thinking about it very carefully is actually a really good way to design better architectures if you're going to be designing architectures. So basically the problem with vanishing gradients is, like, let's say we have a prediction task where we're calculating a regression. We're inputting a whole bunch of tokens and then calculating a regression at the very end using a square error loss function. If we do something like this, the problem is if we have a standard RNN, when we do backprop, we'll have a big gradient, probably for the first RNN unit here. But every time, because we're running this through some sort of nonlinearity, if we, for example, if our nonlinearity is a tan h function, the gradient of the tan h function looks a little bit like this. And here, if I am not mistaken, this peaks at 1, and everywhere else it's 0. And so because this is peaking at 1, everywhere else at 0, let's say we have an input way over here, like minus 3 or something like that. If we have that, that basically destroys our gradient. Our gradient disappears for that particular unit. And, you know, maybe one thing that you might say is, oh, well, you know, if this is getting so small because this only goes up to 1, let's do like 100 times tan h as our activation function. We'll do 100 times tan h, and so now this goes up to 100, and now our gradients are not going to disappear. But then you have the opposite problem. You have exploding gradients where it goes up by 100 every time. It gets unmanageable and destroys your gradient descent and stuff. So basically, we have this problem because if you apply a function over and over again, your gradient gets smaller and smaller smaller and smaller, bigger and bigger every time you do that, and you have the vanishing gradient or exploding gradient problem. It's not just a problem with nonlinearities, so it also happens when you do your weight matrix multiplies and other stuff like that. Basically, anytime you modify the input into a different output, it will have a gradient, and so it will either be bigger than 1 or less than 1. So I mentioned this is a problem for RNNs. It's particularly a problem for RNNs over long sequences, but it's also a problem for any other model you use. And the reason why this is important to know is if there's important information in your model, finding a way that you can get a direct path from that important information to wherever you're making a prediction often is a way to improve your model performance. And on the contrary, if there's unimportant information, if there's information that you think is likely to be unimportant, putting it farther away or making it a more indirect path so the model has to kind of work harder to use it is a good way to prevent the model from being distracted by like tons and tons of information, some of it which may be irrelevant. So it's a good thing to know about in general for model design. So how did RNNs solve this problem of the vanishing gradient? There's a method called long short-term memory. And the basic idea is to make additive connections between time steps. And so addition is the only addition, or kind of like the identity, is the only thing that does not change the gradient. It's guaranteed to not change the gradient because the identity function is like f of x equals x. And if you take the derivative of this, it's 1. So you're guaranteed to always have a gradient of 1 according to this function. So long short-term memory makes sure that you have this additive input between time steps. And this is what it looks like. It's not super, super important to understand everything that's going on here, but just to explain it very quickly, this C here is something called the memory cell. It's passed on linearly like this. And then you have some gates. The update gate is determining whether you update this hidden state or how much you update given this hidden state. This input gate is deciding how much of the input you take in. And then the output gate is deciding how much of the output from the cell you basically push out after using the cell. So It has these three gates that control the information flow, and the model can learn to turn them on or off, or something like that. So that's the basic idea of the LSTM. And there's lots of other like variants of this, like gated recurrent units that are a little bit simpler. But the basic idea of an additive connection plus gating is something that appears a lot in many different types of architectures. Any questions here? Another thing I should mention that I just realized I don't have on my slides, but it's a good thing to know, is that this is also used in deep networks and multi-layer networks. And so basically, LSTMs, this is time. LSTMs have this additive connection between the memory cell where you're always adding this into whatever input you get. And then you get an input and you add this in, you get an input. And so this makes sure you pass your gradients forward in time. There's also something called residual connections, which I think a lot of people have heard of if you've done a deep learning class or something like that. But if you haven't, they're a good thing to know. Residual connections are if you run your input through multiple layers. Like let's say you have a block here. Let's call this an RNN for now because we know about RNNs already. So RNN. So this connection here is called the residual connection, and basically it's adding an additive connection before and after layers. So this allows you to pass information from the very beginning of a network to the very end of a network through multiple layers. And it also is there to help prevent the gradient vanishing problem. So like in a way you can view LSTMs. What LSTMs are doing is preventing loss of gradient in time, and these are preventing loss of gradient as you go through like multiple layers of the network. And this is super standard. This is used in all like transformer models and Llama and GPT and whatever else. Cool. Any other questions about that? Okay. Cool. So next I'd like to go into convolution. One thing I should mention is RNNs or RNN style models are used extensively in very long sequence modeling. And we're going to talk more about like actual architectures that people use to do this, usually in combination with attention-based models, but they're used in very long sequence modeling. Convolutions tend to be used in a lot in speech and image processing. And the reason why they're used a lot in speech and image processing is because when we're processing language, we have like, this is wonderful. Like this is wonderful is 3 tokens in language. But if we look at it in speech, it's going to be like many, many frames. So kind of the semantics of language is already kind of like, if you look at a single token, you already get something semantically meaningful. But in contrast, if you're looking at like speech or you're looking at pixels and images or something like that, you're not going to get something semantically meaningful. So convolution is used a lot in that case. And also you could create a convolutional model over characters as well. So what is convolution in the first place? As I mentioned before, basically you take the local window around an input and you run it through basically a model. And a good way to think about it is it's essentially a feed-forward network where you concatenate all of the surrounding vectors together and run them through a linear transform like this. So you concatenate xt minus 1, xt plus 1. Convolution can also be used in autoregressive models. And normally, like we think of it like this. So we think that we're taking the previous one, the current one, and the next one, and making a prediction based on this. But this would be good for something like sequence labeling, but it's not good for something like language modeling, because in language modeling, we can't look at the future, right? But there's a super simple solution to this, which is you have a convolution that just looks at the past, basically, and predicts the next word based on the current word in the past. So here you would be predicting the word movie. This is actually essentially equivalent to the feed-forward language model that I talked about last time. So you can also think of that as a convolution, a convolutional language model. So whenever you say feed-forward or convolutional language model, they're basically the same, modulo some details about striding and stuff, which I'm going to talk about at the end of the class today. Cool. I covered convolution very briefly because it's also the least used of the three sequence modeling things in NLP nowadays. But are there any questions there, or can I just run into attention? Okay, cool. I'll go into attention next. So the basic idea about attention is that we encode each token in the sequence into a vector. So we have an input sequence that we'd like to encode over, and we perform a linear combination of the vectors weighted by attention weights. And there's two varieties of attention that are good to know about. The first one is cross attention, where each element in a sequence attends to elements of another sequence. And this is widely used in encoder-decoder models, where you have one encoder and you have a separate decoder. These models, the popular models that are like this, that people still use a lot, are T5, is an example of an encoder-decoder model, or MBART is another example of an encoder-decoder model. But basically, the way cross-attention works is we have, for example, an English sentence here, and we want to translate it into a Japanese sentence. And so when we output the first word, we would mostly upweight this, or sorry, we have a Japanese sentence and we would like to translate it into an English sentence, for example. So when we generate the first word, kore in Japanese means this. So in order to output the first word, we would first do a weighted sum of all of the embeddings of the Japanese sentence. And we would focus probably most on this word up here, kore, because it corresponds to the word this. In the next step of generating an output, we would attend to different words because different words correspond to is. So you would attend to desu, which corresponds to is. When you output and, actually there's no word in the Japanese sentence that corresponds to and, so you might get a very blob, inattention weight that doesn't look very, that looks very smooth, not very peaky. And then when you do example, you'd have strong attention on the word that corresponds to example. There's also self-attention. And self-attention, basically what it does is each element in a sequence attends to elements of the same sequence. And so this is a good way of doing sequence encoding, just like we used RNNs, bi-RNNs, convolutional neural networks. And so the reason why you would want to do something like this, just to give an example, let's say we wanted to run this. We wanted to encode the English sentence before doing something like translation into Japanese. And if we did that, this, maybe we don't need to attend to a whole lot of other things because it's kind of clear what this means. But is the way you would translate it would be rather heavily dependent on what the other words in the sentence. So you might want to attend to all the other words in the sentence, say, oh, this is co-occurring with this and example. And so if that's the case, then, well, we would need to translate it in this way, or we need to handle it in this way. And that's exactly the same for, any other sort of disambiguation style task. So yeah, we do something similar like this. So basically cross-attention is attending to a different sequence. Self-attention is attending to the same sequence. So how do we do this mechanistically in the first place? So like, let's say we're translating from Japanese to English. We would have, and we're doing it with an encoder-decoder model, where we have already encoded the input sequence, and now we're generating the output sequence with for example, a recurrent neural network. And so if that's the case, we have I hate like this, and we want to predict the next word. So what we would do is we would take the current state here, and we use something called a query vector. And the query vector is essentially the vector that we want to use to decide what to attend to. We then have key vectors, and the key vectors are the vectors that we would like to use to decide which ones we should be attending to. And then for each query key pair, we calculate a weight. And we do it like this. This gear here is some function that takes in the query vector and the key vector and outputs a weight. And notably, we use the same function every single time. This is really important, again, because like RNNs, that allows us to extrapolate to unlimited length sequences, because we only have one set of, we only have one function no matter how long the sequence gets. So we can just apply it over and over and over again. Once we calculate these values, we normalize so that they add up to 1 using the softmax function. And basically, in this case, that would be like 0.76, et cetera, et cetera. Oops. So step number 2 is, once we have these attention values here, notably, these values aren't really probabilities, despite the fact that they're between 0 and 1 and they add up to 1, because all we're doing is we're using them to combine together multiple vectors. So we don't really normally call them attention probabilities or anything like that. I just call them attention values or normalized attention values. But once we have these attention weights, we have value vectors. And these value vectors are the vectors that we would actually like to combine together to get the encoding here. And so we take these vectors, we do a weighted sum of the vectors and get a final sum here. And we can take this sum and use it in any part of the model that we would like. And so attention is very broad. It can be used in any way. Now, the most common way to use it is just have lots of self-attention layers, like in something in a transformer, but you can also use it in a decoder or other things like that as well. This is an actual graphical example from the original attention paper. I'm going to give some other examples from transformers in the next class, but basically you can see that the attention weights for this English to French, I think it's English to French translation task, basically overlap with what you would expect if you can read English and French. It's kind of the words that are semantically similar to each other. It even learns to do this reordering in an appropriate way here. And all of this is completely unsupervised. So you never actually give the model information about what it should be attending to. It's all learned through gradient descent. And the model learns to do this by making the embeddings of the key and query vectors closer together. Cool. Any questions? Okay. So next, I'd like to go a little bit into how we actually calculate the attention score function. So that's the little gear that I had on my slide before. So here, Q is the query and K is the key. The original attention paper used a multi-layer neural network to calculate this. So basically what it did is it concatenated the query and key vector together, multiplied it by a weight matrix, calculated a tanh, and then ran it through a weight vector. So this is essentially very expressive. It's flexible. It's often good with large data, but it adds extra parameters and computation time to your calculations here. So it's not as widely used anymore. The other thing which was proposed by Luong et al. Is a bilinear function. And a bilinear function, basically what it does is it has your key vector, it has your query vector, and it has a matrix in between them like this. And then you calculate the output. So this is nice because it basically can transform the key and query together here. People have also experimented with dot product, and the dot product is basically query times key, query transpose times key, or query dot key. This is okay, but the problem with this is then the query vectors and the key vectors have to be in exactly the same space, and that's kind of too hard of a constraint, so it doesn't scale very well if you're working hard, if you're like training on lots of data. Then the scaled dot product, here, one problem is that the scale of the dot product increases as the dimensions get larger. And so there's a fix to scale by the square root of the length of one of the vectors. And so basically you're multiplying, you're taking the dot product, but you're dividing by the square root of the length of one of the vectors. Does anyone have an idea why you might take the square root here? If you've taken a machine learning or maybe statistics class, you might have an idea. Any ideas? Yeah.
Define normalization to make sure that because otherwise it will impact the result because we want to normalize it to be one.
Yes, so we do want to normalize it. And so that's the reason why we divide by the length, and that prevents it from getting too large. Specifically, does anyone have an idea why you take the square root here, as opposed to dividing just by the length overall? So this is pretty tough, and actually, I didn't know one of the last times I did this class, and had to actually go look for it. But basically, the reason why is because if you have a whole bunch of random variables, so let's say you have a whole bunch of random variables, no matter what kind they are, as long as they're from the same distribution, they're IID, and you add them all together, then the variance, I believe, yeah, the variance of this, variance standard deviation, maybe standard deviation of this goes up square root. Yeah, I think standard deviation goes up dividing by something that would divide by this the standard deviation here. So it's made like normalizing by that. So that's actually, I don't think explicitly explained in the attention is all you need paper, the Vaswani paper where they introduce this, but that's the basic idea. In terms of what people use most widely nowadays, they are basically doing this. So they're taking the hidden state from the keys and multiplying it by a matrix, the hidden state by the queries and multiplying it by a matrix. This is what is done in transformers. And and then they're using this to they're normalizing it by this square root here. And so this is essentially a bilinear model. It's a bilinear model that is normalized. They call it scaled dot product attention, but actually because they have these weight matrices, it's a bilinear model. So that's the most standard thing to be used nowadays. Cool. Any questions about this part? Okay. So finally, when you actually train the model, as I mentioned before, right at the very beginning, when we're training an autoregressive model, we don't want to be referring to the future, to things in the future, because then, basically we'd be cheating and we'd have a non-probabilistic model. It wouldn't be good when we actually have to generate left to right. And so we essentially want to prevent ourselves from using information from the future. And in an unconditioned model, we want to prevent ourselves from using any information in the future here. In a conditioned model, we're okay with doing kind of bidirectional conditioning here to calculate the representations, but we're not okay with doing it on the target side. So basically what we do is we create a mask that prevents us from attending to any of the information in the future when we're calculating the representations of the current thing, word. And technically, how we do this is we have the attention values, like 2.1, attention 0.3, and attention 0.5 or something like that. These are eventually going to be fed through the softmax to calculate the attention values that we use to do the weighting. So what we do is any ones we don't want to attend to, we just add negative infinity or add a very large negative number. So we cross that out and set this to negative infinity. And so then when we take the softmax, basically the value goes to 0 and we don't attend to it. So this is called the attention mask, and you'll see it when you have to implement attention. Cool. Any questions about this? Okay, great. So next I'd like to go to applications of sequence models. There's a bunch of ways that you can use sequence models of any variety. I wrote RNN here arbitrarily, but it could be convolution or a transformer or anything else. So the first one is encoding sequences. And essentially, if you do it with an RNN, this is one way you can encode a sequence. Basically, you take the last value here, and you use it to encode the output. This can be used for any sort of like binary or multi-class prediction problem. It's also right now used very widely in sentence representations for retrieval. So for example, you build a big retrieval index with these vectors, and then you do a vector you also encode a query and you do a vector nearest neighbor search to look up the most similar sentence here. So these are two applications where you use something like this. Right on this slide, I wrote that you use the last vector here, but actually a lot of the time it's also a good idea to just take the mean of the vectors or take the max of all of the vectors. In fact, I would almost say that that's usually a better choice if you're doing any sort of thing where you need a single vector, unless your model has been specifically trained to have good like output vectors from the final vector here. So you could also just take the mean of all of the purple ones. Another thing you can do is encode tokens for sequence labeling. This can also be used for language modeling. And what do I mean it can be used for language modeling? Basically, you can view this as first running a long sequence encoding, and then after that, making all of the predictions. It's also a good thing to know computationally because often you can do sequence encoding kind of all in parallel. And yeah, actually, I said I was going to mention that, but I don't think I actually have a slide about it. But one important thing about RNNs compared to convolution or convolution or attention is RNNs, in order to calculate this RNN, you need to wait for this RNN to finish. So it's sequential, and you need to go like here, and then here, and then here, and then here, and then here. And that's a pretty big bottleneck because things like GPUs or TPUs, they're actually really good at doing a bunch of things at once. And so attention, even though its asymptotic complexity is worse, O of n squared, just because you don't have that bottleneck of doing things sequentially, it can be way, way faster on a GPU because you're not wasting your time waiting for the previous thing to be calculated. So that's actually why transformers are so fast. Transformers and attention models are so fast. Another thing to note, so that's one of the big reasons why attention models are so popular nowadays, because they're fast to calculate on modern hardware. Another reason why attention models are popular nowadays, does anyone have an idea about another reason? It's based on how easy they are to learn, and there's a reason why. And that reason why has to do with something I introduced in this lecture earlier. I'll give a hint. Gradients, yeah. More specifically, what's nice about attention with respect to gradients or vanishing gradients? Any ideas? Let's say we have a really long sentence that's like x1, x2, x3, x4, x200 over here. And in order to predict x200, you need to pay attention to x3. Any ideas? Another hint, how many nonlinearities do you have to pass through in order to pass that information from x3 to x200? In a recurrent network, or attention.
In the recurrent network, it should be 197.
Yeah, in a recurrent network, it's basically 197 or maybe 196. I haven't paid attention, but every time you pass it to the hidden state, it has to go through a nonlinearity. So it goes through like 197 nonlinearities. And even if you're using an LSTM, it's still, the LSTM hidden cell is getting information added to it and subtracted to it and other things like that. So it's still a bit tricky. What about attention? Yeah, basically one time. So attention, in the next layer here, you're passing it all the way, you're passing all of the information directly in, and the only qualifying thing is that your weight has to be good. It has to find a good attention weight so that it's actually paying attention to that information. So this is actually discussed in the Vaswani et al. Attention is all you need paper that introduced transformers. Convolutions are kind of in the middle. So like, let's say you have a convolution of length 10, and then you have two layers of it. If you have a convolution of length 10, or yeah, let's say you have a convolution of length 10, you would need basically, you would pass from 10 previous ones, and then you would pass again from 10 previous ones, and then you would have to go through like 16 or like, I guess almost 20 layers of convolution in order to pass that information along. So it's kind of in the middle of RNNs and LSTMs. Sorry, RNNs and attention models. Yeah.
Question. So regarding how you have to wait for one RNN before the next one, can you inference on one RNN once it's done, even though the next one's computing off that one?
Yes, yeah, you can do inference. You could as well, so as long as the output doesn't affect the next input. So in this case, because of language modeling or generation, is because the output doesn't affect the next, because the output affects the next input, if you're predicting the output, you have to wait. If you know the output already, you could make the prediction at the same time as calculating this next hidden state. So if you're just calculating the probability, you could do that. And that's actually where transformers or attention models shine. Attention models actually aren't great for generation. And the reason why they're not great for generation is because they're like when you're generating the next token, you still need to wait. You can't calculate in parallel because you need to generate the next token before you can encode the previous. Sorry, you need to generate the next token before you can encode it. So you can't do everything in parallel. So transformers for generation are actually slow. And there are models. I don't know if people are using them super widely now, but there were actually machine translation models that were in production where they had a really big, strong transformer encoder, and then they had a tiny, fast RNN decoder. And if you want a actual reference, there's this deep encoder, shallow decoder. And then there's also the Miriam machine translation toolkit that supports those types of things as well. So it's also the reason why if you're using like the GPT models through the API, that decoding is more expensive, right? Like encoding, I forget exactly, is it 0.03 cents for 1,000 tokens for encoding and 0.06 cents for 1,000 tokens for decoding in like GPT-4 or something like this? The reason why is precisely that, just because it's so much more expensive to run the decoder. Cool. I have a few final things also about efficiency. So these go back to the efficiency things that I talked about last time. Handling mini batching. So what do we have to do when we're handling mini batching? If we were handling mini batching in feed-forward networks, it's actually relatively easy because all of our computations are the same shape. So we just concatenate them all together into a big tensor and run over it. We saw mini batching makes things much faster, but mini batching in sequence modeling is harder than in feed-forward networks. One reason is in RNNs, each word depends on the previous word. Also because sequences are of various lengths. So what we do to handle this is we do padding and masking. So we can do padding like this. So we just add an extra token at the end to make all of the sequences at the same length. If we are doing an encoder-decoder style model, where we have an input, and then we want to generate all of the outputs based on the input, one of the easy things is to add pads to the beginning. And then, so yeah, it doesn't really matter, but you can add pads to the beginning so they're all starting at the same place, especially if you're using RNN style models. Then we calculate the loss over the output, for example. We multiply the loss by a mask to remove the loss over the tokens that we don't care about. And we take the sum of these. And so luckily, most of this is implemented in, for example, PyTorch or Hugging Face transformers already, so you don't need to worry about it. But it is a good idea to know what's going on under the hood if you want to implement anything unusual. And also, it's good to know for the following reason also, which is bucketing and sorting. So if we use sentences of vastly different lengths and we put them in the same mini batch, this can waste a really large amount of computation. So like, let's say we're processing documents or movie reviews or something like that. And you have most movie reviews are like 10 words long, but you have one movie review in your mini batch of 1,000 words. So basically what that means is you're padding most of your sequences 990 times to process 10 sequences, which is like a lot of waste, right? Because you're running them all through your GPU and other things like that. So one way to remedy this is to sort sentences. So similarly linked sentences are in the same batch. So you first sort before building all of your batches, and then that makes it so that similarly sized ones are in the same batch. This goes into the problem that I mentioned before, but only in passing, which is, let's say you're calculating your batch based on the number of sequences that you're processing, if you say, okay, I want 64 sequences in my mini batch, if most of the time those 64 sequences are 10 tokens, that's fine. But then when you get the one mini batch that has 1,000 tokens in each sentence or each sequence, suddenly you're going to run out of GPU memory and your like training is going to crash, right? Which is, you really don't want that to happen when you started running your homework assignment and then went to bed and then wake up and it crashed, 15 minutes into computing or something. So this is an important thing to be aware of practically. Again, this can be solved by a lot of toolkits. Like I know FairSeq does it, and Hugging Face does it if you set the appropriate settings, but it's something you should be aware of. Another note is that if you do this, it's reducing the randomness in your distribution of data. So stochastic gradient descent is really heavily reliant on the fact that your ordering of data is randomized, or at least it's distributed appropriately. So it's something to definitely be aware of. So this is a good thing to think about. Another really useful thing to think about is strided architectures. Strided architectures appear in RNNs, they appear in convolution, they appear in transformers or attention-based models. They're called different things in each of them. So in RNNs, they're called pyramidal RNNs. In convolution, they're called strided architectures. And in attention, they're called sparse attention, usually. They all actually kind of mean the same thing. And basically what they mean is you have a multi-layer model. And when you have a multi-layer model, you don't process every input from the previous layer. So here's an example. Like let's say you have a whole bunch of inputs. Each of the inputs is processed in the first layer in some way. But in the second layer, you actually input, for example, 2 inputs to the RNN, but you skip. So you have one state that corresponds to state number 1 and 2, another state that corresponds to state number 2 and 3, another state that corresponds to state number 3 and 4. So what that means is you can gradually decrease the number, like the length of the sequence every time you process. So this is a really useful thing to do if you're processing very long sequences. So you should be aware of it. Cool. Everything okay? Okay. The final thing is truncated backpropagation through time. And truncated backpropagation through time, what this is doing is basically you do backprop over shorter segments, but you initialize with the state from the previous segment. And the way this works is, like, for example, if you're running an RNN, you would run the RNN over the previous segment. Maybe it's length 4, maybe it's length 400. It doesn't really matter, but it's a coherently linked segment. And then when you do the next segment, what you do is you only pass the hidden state, but you throw away the rest of the previous computation graph and then walk through like this. So you won't actually be updating the parameters of this based on the result, the loss from this, but you're still passing the information. So this can use the information from the previous state. So this is an example from RNNs. This is used pretty widely in RNNs, but there's also a lot of transformer architectures that do things like this. The original one is something called Transformer XL that was actually created here at CMU, but this is also used in the new Mistral models and other things like this as well. So it's something that's still very much alive and well nowadays as well. Cool. That's all I have for today. Are there any questions people want to ask before we wrap up? Yeah.
For the condition.
Yep.
What exactly? Having a hard time understanding source X or Y. What do they represent?
Yeah. So for condition prediction, what is source X and target Y? I think I kind of maybe carried over some terminology from machine translation by accident. Maybe it should be input X and output Y. That would be a better way to put it. And so it could be anything. For translation, it's like something in the source language and something in the target language. So like English and Japanese. If it's just a regular language model, it could be something like a prompt and the output. Yeah.
And so for unconditional, prediction.
Yep.
Like, when the example of that would be. Yeah, I'm not having a hard time.
So for unconditioned prediction, that could just be straight up language modeling, for example. So language modeling with not necessarily any prompt. Okay, thanks. Anything else? Okay, great. Thanks a lot. I'm happy to take questions up here too.